Hi, my name is Gavin Rossi, and I will be doing a presentation on finite impulse response design through windowing. So first we want to ask ourselves, what even is this? What's the point? Well, we do this windowing design because what we can create are these digital filters, and these digital filters can transmit certain bands of frequencies, attenuate other bands, and that in all allows us to control the signal that we're transmitting. We can bend it to be whatever we want it to be for the system that we need to use it for. So how do we go about creating this type of shape? Well, the first step is to truncate a math function to some degree. And depending on how much you truncate it, we find that the more truncations that are done, the steeper the roll-off becomes, the narrower the passband becomes a little bit, and the more attenuation you get in the blocking band. Now, there's also another way to affect the shape of the digital filter, and that's just choose which math function you're going to use and truncate. So depending on which function that is, that can again affect the passband shape, the attenuation shape, and a little bit of the roll-off. So with these two things in mind, depending on which math function you pick and how you're going to truncate it, you likely can create any filter that you really need, any shape that can block at any frequency or transmit with, like, you can pick the gain, like the passband region, the 1 dB bandwidth, the 3 dB bandwidth, like the possibilities are endless. Now, it's worth mentioning that you can't just use any filter for any signal. We need to know what these filters are going to be used for and what the original signal is going to be, because if we have say a 19-tap Honig filter, which cuts off pretty soon in the frequency band, and then you have a signal being passed through that like extends out to 4,000 kilohertz, you're going to cut off a lot of that signal that you're trying to transmit, and then all of a sudden you have a signal that's significantly worse, and it's almost not worth filtering in the first place. So with that being said, let's look at some of these filters that we can create. So this is a 7-tap and a 19-tap rectangular filter. Looking at the shape, you can clearly see that the 19-tap filter has more attenuation, which is what was expected. And the bandwidth also is just a little bit narrower, at least the minus 20 dB bandwidth. So when applying this filter to a signal, we should expect that the 19-tap is going to filter out a little bit of the higher noise, and the 7-tap is going to still filter it, but to not as well of a degree. Now let's see it in real life. So this is the original signal that we are going to be filtering. Now let's filter it through the 7-tap filter and then the 19-tap filter. Now, I would say that the 7-tap and 19-tap are both very similar in terms of the overall sound that you get. However, I think the 19-tap has just a little bit more of what made the original signal. And you can also, I mean, it was a little bit more sharp. It just sounded more like what it was supposed to be. And you can see this in the spectrum response. We have these spikes happening at around 4 kilohertz, which also happens in the original signal that we don't see with the 7-tap filter. However, consequently, the 19-tap does attenuate more at the higher frequencies, which is a consequence that we'll see of picking more taps. So we get better transmission in the mid-range frequencies and then more attenuation at the end. However, for this signal, it seems that the 19-tap is clearly working for what we're trying to transmit. Now, let's look at the Hahn type window. So the difference between, or maybe one main takeaway or difference from the Hahn than the rectangular is that we see a gain with the Hahn filter, which is really interesting. So that means that at the lower frequencies, we should expect almost a more bassy sound coming through. And we also see a little bit more attenuation going down. But the most interesting part is probably that when we add the taps, the 19-tap Hahn significantly reduces in bandwidth. So this might not be ideal for the signal that we were trying to use, but let's say we do have a signal that is low in frequency, we can definitely use the Hahn and it will filter out everything else. And if it's within 1 kilohertz, it seems that it would transmit it very well. But let's see it with this signal. Here's the original sound again. Here is the 7-tap and the 19-tap. So we're seeing that the original signal is being filtered out a little more than it should. It sounds a little bit muffled. It almost sounds like clay is in the trunk of a car, which is not really good. It's not really what we're going for. And in addition, it doesn't seem that it's filtering out the noise that well, as because you can still hear the fanning in the background. But one benefit of the 19 tap, as we can see, is we get an extremely flat attenuation band. So again, if we have a signal with a little bit less in the frequency range, this 19 tap would probably do great, but because it's cutting into the actual signal that we're trying to transmit, we get a worse muffled sound with more bassy undertones. So it doesn't seem like the ideal call. And here's just an overlay of the two filters. You can see the 7-tap rect and Han are both pretty similar. The main difference with the Han is that it has gain for the 7-tap, and then with the 19-tap, you see an obvious reduce in bandwidth for the Han as compared to the rectangle. But all in all, it seems the rectangle is the winner. So how do we even come across these results? Well, we took the original signal, sampled it, and then we created a digital filter based off mathematical function and truncation. Then we pass this original signal through this function, and then we essentially listened to and plotted the modified sample signal. And then we repeated this for the different types of filters that we use. And that's my presentation. Thank you.